inverse functions. I wonder if you can recall grade 8 where functions were introduced for the very first time, probably even before grade 8. It was probably grade 5 or 6 or 7, whereby you had an input value. You used an input value along with a specific set of rules to get you an output value. Eventually, we attached the word function to this kind of machine, and many teachers related it to baking a cake. Your input can be your eggs and your flour and your sugar, and you mix it all together in a very specific recipe which represents the function, and as a result, you get a cake being the output value. Now, an inverse function is merely a magical way to undo that process. Imagine you had an incredible machine or a super advanced oven into which you could insert a fully baked cake, and out of it would pop the raw ingredients. It could tell you what the original input values were if you give it the output values. Basically, we are inverting the process. We're undoing the maths. And before I harp on too long about that, I'm just going to go into the basic idea behind an inverse function. It is the reflection of a function in the line y equals x, because y equals x is telling you that you are making your y's an x and you're making your x a y. You are inverting the variables. Today we're going to go over the inverse of a straight line, but we will go through all the functions throughout the rest of the week. So the inverse of a straight line. Let's imagine any straight line on the Cartesian plane. Whenever you see a sketch of a straight line, get a rough idea. You can see, the y-intercept would be positive, but the gradient of this line would be negative. So y equals a negative half x plus 1 is a reasonable equation for this function. Now, if I've just told you that the inverse function is the reflection of the function in the line y equals x, let's imagine this dotted line to be y equals x. How do I know that is y equals x? Because the angle formed between the dotted line and the x-axis is 45 degrees always. So it's very easy to sketch the line y equals x. It goes through the origin and it forms 45 degrees between the x-axis and itself. It cuts that 90 degrees between the y and x-axis smack bang in the middle. Now, if we need to reflect this blue line over the line y equals x, you can actually take a mirror and pop it against the dotted line and have a look into the mirror to see what the graph should look like. You can even use any reflective object. Sometimes if you lock your cell phone and put your cell phone screen against the line y equals x, you'll be able to see what the inverse function will look like. Now, this y equals x is the magic machine that inverts the function. If you were to reflect the blue over the dotted, you would get that green line right there. And that line is called the inverse of the blue line, y equals a negative half x plus 1. Now, I'm sure you're wondering, what is the equation of this line? Y equals what? And that's what we're going to cover on the next slide. So in order to find the equation of an inverse function, all you need to do is reflect the function, but algebra style. And to do it algebra style is not to imagine the line y equals x, but to merely swap the x and y variables of the original function. But because we are used to seeing functions with y, the subject of the formula, and the rest of the equation in terms of x, don't forget the second bullet point. Make y the subject of the formula once you've swapped the x and y variables of the original function. So for this previous function, y was equal to minus a half x plus 1. So step number 1, let's swap our x and y variables. All you did was instead of a y, you wrote x. Instead of an x, you wrote y. Now that represents the inverse function. However, in order to be able to sketch it on the exact same Cartesian plane, we are going to need to make y the subject of the formula. Also, take a note that the inverse function notation has a little minus 1. F to the power of -1. That merely means inverse function. So if fx is your original function, the inverse of f will be denoted with a -1 over there. Let's carry on making y the subject of the formula. I've taken the +1 over to the left-hand side of the equation, so it becomes negative, and I've neatened up the right-hand side by multiplying my negative, my 1, and my y to the top of the fraction, minus y over 2. I've got rid of my 2 as a denominator by multiplying every single term by 2. Now we're left with -y on the right-hand side of the equation. Let's swap every single term in this equation. Their signs will change, and we end up with the equation of the inverse function. So y equals -2x plus 2 is the equation of that green line that we sketched on the previous slide. So let's just recap. To sketch the inverse of a function, you just have to reflect the function in the line y equals x. So it's a very physical or visual approach. If you can sketch a dotted line, y equals x, and then reflect that inverse over that line, you have successfully sketched the inverse of a function. However, it's a little bit more complex to find that actual equation of the inverse function, but all you need to do is remember these 2 steps. Number 1, swap the x and y variables. Number 2, solve for y. To assist you in the reflection of a graph over the line y equals x, you can note the following 3 points, and it accounts for every single inverse function. An x-intercept of the original function will become a y-intercept of the reflected function or the inverse function. The domain of the original function will become the range of the inverse function. Later on, when we're dealing with hyperbole or exponential graphs, a vertical asymptote will become a horizontal asymptote, and vice versa. In other words, the y-intercept of the original function will be the x-intercept of the inverse function, etc. So let's just go over this concept with the example that we've been working with today. If I struggled to reflect this with my mere eyesight, if I couldn't see what the reflection of this blue line would look like, let's just find the x and y intercept of this blue line and reflect them and swap them around for the inverse function. So for an x-intercept, we make y equals 0, and if you were to solve for this graph's x-intercept, you'd see that the x-intercept would be 2. Y-intercept is super obvious, it's +1, so we've labeled it 2 and 1 as your x-intercept and your y-intercept. So that means if 2 is the x-intercept of the blue graph, an x-intercept will become a y-intercept. 2 will be the y-intercept of the green graph. So up here at 2, we have the y-intercept of the green graph. And doesn't that make sense considering on the previous slide we found the equation of the green graph and it was -2x plus 2. So the y-intercept was 2. So if the y-intercept of the original function was a number 1, the x-intercept of the inverse function will be a number 1. So our x-intercept became our y-intercept, and our y-intercept became our x-intercept. Now let's connect the green 2 to the green 1, and voila! Once again, we have the inverse function neatly sketched. Look at that little point of intersection. Isn't that quite cute? The point of intersection of the inverse function and the original function occurs on that line, y equals x. That's going to help you complete your homework for the day, which has just appeared on the screen. So it's a quick activity just to warm you up for inverse functions before we tackle the actual definition, well, a deeper, more intricate definition of inverse functions. After you do the quick homework exercise, please read page 53 because that will give you background information for the next lesson when we get into the nitty-gritties about what is a function. Thank you.